Yeah, hi guys. So this is then continuation with the numerical problems which we were solving. So I'm going to discuss the numerical number 11 and 11 12. So 11, what it talks about, let's first try to understand what the problem is all about. The problem talks that a ball moves on a smooth floor in a straight line. A ball moves on a smooth floor on a straight line, right? Ball. This is ball. This ball moves on a smooth floor in a straight line with a uniform velocity of 10 meter per second. At what velocity it is moving? It is given that it is moving at a velocity of 10 meter per second. And as per the direction convention, we are saying if the ball is moving right, we will take it positive, and if the ball is moving in the left direction, we will take it negative. So as per the direction convention, we are going. At 6 seconds, right? And it is given that this velocity is uniform velocity. At t equal to 6 seconds, this one please. Yeah, at t equal to, so the ball is moving with a uniform velocity of 10 meter per second for 6 seconds. At t equal to 6 seconds, the ball hits a wall and come back along the same line. Here is the ball went and strike and come back to the same along the same line with the same speed. So now this time after striking it, it is moving with the same speed but in the opposite direction. So obviously it happens, right? 10 meter per second, right? Draw the velocity time graph and use it to find the time distance, the total distance traveled by the ball and the displacement. So from this is the problem, right? So let's draw the velocity time graph. So what I have done is that it is already given in the problem that for first 6 seconds the ball is moving with a uniform velocity of 10 meter per second, which are shown here. 10 meter per second, 10, right? For first 6 seconds it's moving with a uniform velocity. That means the line has to be horizontal. After that it strikes the wall and its velocity get reversed. It is started moving with the in the opposite direction with the same speed. That means magnitude of velocity is same, but direction got changed. So this time we have to flip onto at t equal to 6 seconds. There are two velocities, you can say. Actually, it is a conversion. At t equal to 2 seconds, it strikes the wall. So that's why it is 10 meter per second, and it started moving in the opposite direction. So it is minus 10 meter per second, right? And it took again the same amount of time. That means it took from 6 seconds to 12 seconds to reach the starting position. Now the ball reached this position, starting position in again the same time. Obviously it is same, right? So they are asking about what they are asking. They are asking draw the velocity time graph. So this is the velocity time graph. Okay, velocity time graph we done. Now what they are asking about from that? Used to find the total distance traveled by the ball and its displacement. So as we discussed earlier, with the help of the velocity time graph, we can find out the displacement and total distance. So they are asking us to calculate the total distance traveled by the ball, right? So what is the total distance traveled by the ball? So we will write total distance traveled by the ball. Total distance is equal to, see, let us name this. This is origin. So we are naming it A, we are naming it B, we are naming it C, we are naming it D, we are naming it E, we are naming it F, we are naming it G. Okay. So we are calculating total distance. That means we are calculating Net scalar quantity. Net scalar quantity is the algebraic sum. Is the algebraic sum of the constituent scalar quantity. Algebraic sum of the algebraic sum of the constituent distances. Constituent distances. Right? Constituent distances. So velocity time graph. Area of the velocity time graph gives us distance, right? It's a motion in one dimension. So distance we can calculate. So while calculating the total distance, we have to keep in mind that we have to do algebraic sum of the constituent distances. This is the algebraic sum. So what we mean by algebraic sum? Algebraic sum means we have to simply add the area of rectangle ABCD, right? Plus we have to do plus. Algebraic sum means everything you have to do plus. Whether it is lying below the time axis or up the time axis, it doesn't matter because we are calculating the algebraic sum, right? And area of rectangle you can draw this way. DEFG. So we know how to calculate the area of the rectangle. There are 6 into 10, right? Base into height. 6 into 10 plus what? 6 into 10. It is coming 60 plus 60, 120 meter. Right? And how about the net total displacement or the net displacement? What is the total displacement? Total displacement. What is the total displacement? Total displacement or net displacement, whatever you say, is equal to vector sum, because displacement is a vector quantity. So the net vector quantity is vector sum of the constituent displacements. Okay, in this case we have to take care of one thing, that the area which is lying up the time axis, that we have to take area of rectangle ABCD, right? ABCD minus, this time we will do minus. Why? Because we are finding out vector sum. Vector sum means direction makes sense. So if the area is lying below the time axis, we have to do minus that area. Area of rectangle DEFG. Now we can reuse this value which we have calculated earlier. So it is coming 6 into 10 minus 6 into 10, and it will give you how much? 60 minus 60, 0 meter. So body, since the body returned to its original position, starting position, that's why the displacement is 0, right? And since the distance is a scalar quantity, so it is algebraic sum. So that's why distance cannot be 0. When a body moves, it becomes 120 meter. Right? Let's jump on to the problem number 12. What it says? It says that this is the problem number 12 graph. So it says that velocity time graph of a particle moving in a straight line. It has already been mentioned that velocity time graph of a particle is moving in a straight line. The velocity time graph of that particular motion is given here, right? So let us first put it here. I'll go and explain this way. Just a moment, please. So here what we have to do is that velocity time graph of a particle which is moving in a straight line. It is already mentioned in the problem statement. Problem number 12. Right? State the nature of motion of the particle. From this velocity time graph, what can we say about the nature of motion? Nature of motion of particle? We can say that part 1. In part 1 it is asking about to comment on the nature of motion. So we can comment that okay, from 0 second to 4 second, right? It is in uniformly accelerating, right? Uniform acceleration. Uniform acceleration, right? Because this we can write. And from 4 to 6 second, 4 second to 6 second, you can say that it is uniform retardation. Retardation. Retardation is when velocity decreases. So see, 0 to 4 second velocity increases, from 4 to 6 second velocity decreases, but both are decreasing at the same, increasing or decreasing at the same rate, right? Because they are constant slope, right? So first part we are done. So they are asking us to do it. Now second part, find the displacement of the particle at t equal to 6 second. Can we find out this? Yes, we can find out. Displacement we have to find out, right? So how to find out the displacement? Displacement we can find out by the area of, let's say it A, B, C, right? Area of triangle ABC. Very simple. ABC, just a moment, please. Area of triangle ABC, right? So area of triangle ABC is what? It is half into base into height. What is the base? Base is 6. And what is the height? Height is 2. So 2 cancel out, right? Here is coming 6 meter. 6 meter is the displacement, right? Find the displacement of the particle at equal to 6 meter with that. So third part it is talking about, does the particle changes its direction of motion? Because in the problem statement it said that this is this graph, the velocity time graph, which is given here. It depicts the motion of a particle along a straight line, right? So when a particle is moving from the starting to end position in a straight line, that graph, this particular graph belongs to this particular motion, right? So what this is asking, does the particle changes its direction of motion in C part, in third part? So what do you think? Does the particle changes its direction of motion? No. Here, what happened? It went away from the. It is going away from the starting position, right? And then it gained certain momentum, of course, at this, and then it seems like they applied a brake kind of thing, right? The particle is moving slowly. It is moving slowly, right? Uniformly retarding, and getting stopped here, right? Velocity becomes 0. So nowhere direction get changed, no, because if direction of motion is changing, that means sign of velocity will change. This will move on to the downside of the time axis, but it remained up of the time axis. So direction of motion is not changed. Direction of motion no change. Direction of motion, is there a change? No change. No change in the direction of motion, right? From this to this, uniform acceleration. From this to this, uniform retardation, right? Uniform acceleration, uniform retardation. That's right. What they are asking about in fourth part. Fourth part, compare the distance traveled by the particle from 0 to 4 seconds. Okay. As t equal to 4 seconds. What is that? We can compare. Okay. It is the area of us name this point B. Area of triangle ABD is perpendicular, of course, right? Area of right angle triangle ABD, right angle triangle ABD, and it is half of what? 4 into 2 is coming 4 meter, right? And what is the distance covered from 4 to 6 seconds? Distance covered from 4 t equal to 4 second to 6 second. What is the distance? That is again area of right angle triangle BDC. BDC. What is that? It is half. What is the base? 4 to 6. It will give you 2. Okay. And what is the height? Height is 2. So it is coming 2 meter. So we can compare, right? We can compare that the S distance covered in t equal to 4 second by distance covered in 4 second to 6 second. It will come 4, 5, 2. So it is 2 is to 1. This is the comparison, right? Fifth part, find the acceleration from 0 to 4 seconds. Okay, fine. Find the acceleration from 0 to 4 seconds, right? So, acceleration from 0 to 4 seconds, let us call it A1, right? 0 to 4, right? So, it is rate of change of velocity upon delta t, right? Okay? What is the rate of change of velocity? Velocity means final velocity F, initial velocity I, final time stamp F minus initial time stamp I. What is that? What is the final time stamp? 0 to 4. Yes. So final time stamp is 4. Initial time stamp is 0. What is the final velocity corresponding to 4 seconds? It is 2. Right? And what is the velocity corresponding to 0 seconds? It is 0. So if you see it carefully, you will find that it is 2 upon 4, which is nothing but 0.5 meter per second, right? And how about the acceleration in second case? Acceleration in second case, they are asking us to calculate the acceleration, the retardation from 4 second to 6 second. 4 second to 6 second, let us calculate the acceleration. Delta V minus delta T, 4 second to 6 seconds they are asking. So, here final time stamp is Ti, right? And initial time stamp is Ti. And this is final velocity minus initial velocity, right? So we know that what is the final time stamp? What is the final time stamp? 4 to 6. So 6 is the final time stamp and 4 is the initial time stamp. What is the velocity? What is the value of the velocity at 6? It is 0. It is dropped to 0, right? So final velocity becomes 0 because it is uniformly retarded. And initial velocity corresponding to 4 is 2. So it is coming, how much? It is coming minus 2 upon 2. So it is retarding. So acceleration is coming minus 1 meter per second. Minus 1 meter per second is the value of the acceleration. That means the particle is retarding at the magnitude of retardation, right? The magnitude of retardation of the particle from 4 to 6 seconds. From 4 to 6 seconds is 1 meter per second. Right? Thank you. That's all.